right, this is a video on antiderivatives and indefinite integrals. So this is our start to get to our formulas that we can use after we've learned what it means to do integration. So we say that we have a function, and we usually use capital, doesn't have to always be that, but capital F of x is an antiderivative for a function little f of x if when you take the derivative of capital X, you get little x, okay? And then the process for finding the antiderivative is anti-differentiation, so kind of working the other direction. When you do indefinite integrals, which we'll see in a second, you actually, when you get antiderivatives, you get an entire family of functions because of the plus c, which we've talked a little bit about in class, because if you have an antiderivative and it had a c in it and then you took the derivative, you wouldn't know that there was ever that constant. So, for example, if we have the function f of x equals 3x squared, we're going to list three functions right here that have that when you take the derivative, you get that 3x squared. Okay, so we're going to list some functions. So clearly x cubed has to be part of it because if you take the derivative of x cubed, you'll get 3x squared. But it could be x cubed plus 5. Because if I take the derivative of f1 of x, I'm going to get 3x squared plus the derivative of 5, which is 0. So it could be x squared minus 2, it could be x cubed minus 2, or x cubed plus a million. Okay, all of those would have a derivative of 3x squared. So what we typically write for the antiderivative is we are going to put usually plus c. So the meaning of these plus c's, these constants, is just the moving or up or down of the functions. So for example, this purple one right here happens to be exactly x cubed plus 5. So it's simply the graph moved up 5. Now, if you think about it, think about what derivatives are. Derivatives are the slopes of the tangent lines. So it doesn't make any difference if this has been translated up or down. The slopes of the tangent lines are not going to change. So all of those graphs on here that are colored on here, all of them would have the same tangent lines, would all have the same slopes in the same spots. They've simply been shifted. Okay, so what plus c means is how much the graph has been shifted up or down c. That's what it means. So let's do some, we're going to kind of find these antiderivatives here by sort of what we call guess and check. So we're just going to think about, this is why we practice so hard doing derivatives, to make it easier for us to figure out the antiderivative, okay? So if we look at g prime of x equals 2x, we're going to think, okay, what would you take the derivative of? And the answer is 2x. Well, that would be x squared. And then we're going to have to add plus c, plus a constant, because I have no idea what the constant might have been. When I take the derivative, the derivative will be 0, so I can't see that. So you're always going to have plus c. So again, here we are with f prime of t, so we want to figure out what would f of t be. Well, we know it has something to do with t cubed, because you're going to put the power in front, lower the power by 1, so there's your t squared. The problem is, if we were to multiply by 3, then we would have a 3 here, so we have to do something to undo that. So undoing it would be divide by 3, and then you'll have plus c again. And you can check that by just doing the derivative, and you'll see how that works. If we have y prime equals 1 over x squared, you can think of this in a lot of ways, but what I like to think about is, things that I know because we've done them a lot. So one of those things is when you take the derivative of 1 over x, you get negative 1 over x squared. That's one of those that we've done a lot. Well, since the derivative of 1 over x gives you negative 1 over x squared, then this must have a negative to counteract that. And then, of course, as always, plus c. Okay? So we're going to do a couple more examples, and then we're going to look at the rules that we have and how we would actually do that to do our antiderivatives. So if we have df d theta equals cosine theta, then f of theta. So we just think to ourselves, what do I take the derivative of that gives me cosine? So that would be sine. And then, of course, plus c, because we don't know what constant could have been there. Now, on this next one, I want you to think through a little bit what you do when you have a power. So the way we would do a derivative is we would multiply by the power in front and then lower the power by 1. Integration is an antiderivative, so we are going to go and do them in reverse order and do sort of the reverse function. So instead of multiplying and lowering the power, we're going to raise the power 1 and divide by the power. So I'm going to put the 2/3 there, and then I'm going to divide by the power of 7/4. And that's going to end up being our rule that we're going to use, is that we are going to raise the power by 1 and divide by the power, because we're going to go in the opposite order and do sort of the inverse relation. Now, what we will learn is that when we're dividing by a fraction, that's the same as multiplying by the reciprocal. So we will typically just go ahead and flip it from the beginning. So normally I would go straight to this step, and then I would simplify it a bit. It's 8 over 21. Of course, you don't really need to do that simplification because you are definitely at the point where you could match it if you needed to. Okay, so let's talk about sort of how we read all of this, and then we're going to look at the rules. So the way we talk about this expression, the expression is read the antiderivative of f with respect to x. So that's one way to read that. Now, this notation is a little bit different. So we've kind of talked about this as we've gone through the year. So we normally wrote dy dx. So this is what I told you was really important. We wrote dy dx. And then I told you about when we did the derivative for ln of u, I said I want you to learn it as du over u. Well, du, writing it that way, is just what we call differential form. And so basically all we've done is we've moved the x over here. And it's actually a method that we're going to use to solve what we call a differential equation, which simply means an equation with a derivative in it. And what we're going to do is put our variables together. So we're going to move the dx over here with the f. And now this is just what we call differential form. And so now if I integrate both sides, I'll end up with what I'm looking for, which is y equals something, because the integral of dy is going to be y, of course, plus c, but that's what that means. That's what that term means. So if I integrate both sides, that's what I'm going to do. So we'll do that later, but that's just kind of to let you know. So when you look at your symbols here, some words that we have to be able to use. So this inside here is called the Enegrand. So that's a big part of on the AP test. Like if the Enegrand is correct, then you know you get points for that. So that's what they're looking for. Did you get the inside right? This variable of integration, this dx, is vitally, 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 vitally important. Some of you will be lazy and you'll decide you don't need to write it because you don't need it, blah, blah, blah. But you do need it, and don't get lazy and not write it, because then you're going to end up getting really mixed up when the variables are different. Okay, so it's really important, just like the way we wrote dy dx, your integral has to have a dx. It is also always at the end. it will never make sense to write integral dx times f of x or something like that, okay? So your integrands start with the integral sign, or your antiderivatives start with the integral sign, end with the dx, and then inside is the integrand. This is your constant of integration. You'll see that a lot. We'll talk about plus c, plus c, plus c. Okay, very important. And this capital F normally, not always, but is called the antiderivative. Okay, it's common to use the capital letter for the lowercase letter that was in the integrand, but that doesn't, it's not like every time you see a capital letter, it's automatically an antiderivative. That's not what that means. Okay, and then the way we read it is the antiderivative of f with respect to x, or we say the integral of f of x dx. The dx, again, super, super, super important. Okay, very, very, very important. And we also call this an indefinite integral. We'll do definite integrals soon. You'll see the difference. It's indefinite, and it's the same thing as the antiderivative. Okay, so both of those things are the same. All right, so now I think on your paper this kind of skips, but that's okay. We want to do these rules first so you can turn your notes till you get to the page that has the basic integration rules. Now, here's the part that I want to mention. To you, it looks like, oh my gosh, she's adding all of these formulas. But let's notice that we're really not adding any. Okay, so really all we're doing is we're recognizing that if I have the integral of 0 dx, well, what would I have taken the derivative of? And the answer would be 0. Well, that would be c. Same thing with the integral of k dx. We're just thinking to ourselves, okay, well, what would you take the derivative of? And the answer would just be a number. Well, that would be kx. Like, for example, if you integrate or you take the derivative of 2x, your answer would be 2. So if I integrate 2 dx, my answer is 2x, and then plus c, because we don't know what might have been there. This rule just says you can pull the constant out in front, just like you can for derivatives, and this one simply says plus and minus, you can just add and subtract and do each integral separately. Those rules are just basically the same. So on the left are the differentiation formulas that relate to that. So again, nothing new really. This looks like a whole bunch of formulas, but again, it's not a bunch of formulas. This one is like super heavy duty, like definitely going to use this a bazillion times. So make sure you know that. And that's the power rule. So you take your power and you add 1 and you divide by that new power and then plus c. That's what you do to do the antiderivative. When you look at all of these functions, notice that all it is, it says, what's the integral of cosine? Well, what did I take the derivative of to get cosine? Sine. So if I know all of my derivative formulas, then there's nothing to these. I would immediately recognize this as something I know because it's asking me, what did I take the derivative of? And the answer is secant squared. So I should know that it's tangent x. And then, of course, always plus c, etc. So all those formulas are really just undoing. Okay, so we didn't really, it's not really 6 new formulas. It's really just, if I know my derivatives, these are just the undoing of them. And then same thing true here. The derivative of e to the x is e to the x. Therefore, the integral of e to the x is e to the x, of course, plus c. For a to the x, the derivative would be a to the x times ln of a. So since we're going in the other direction, we would just divide by ln of a. This is the one that's very important. It's going to come up a lot, and it's the only one where you got to be a little bit careful. So if we are integrating 1 over x dx, your mind might think it's ln of x, but you need to really work hard to say to yourself, it's ln of the absolute value of x, and then plus c. Okay, so it's really important because that's one that gets missed a lot by students because they don't learn it that way, and that's the way you should focus on it. Okay, so when you're integrating, so now you can turn back to this page, often we want to think about, and here's the key, okay, I only know those formulas, that's it. And you're not going to learn very many more formulas. Everything's going to be about how can I rewrite what's inside there to fit a formula that I already know. That's what you're going to end up doing. So if we look at this problem, we can say, okay, 5e to the t, I can move the 5 out in front if I want, and I'm going to separate it because remember with integration, adding and subtracting can be done separately. So I pulled the 5 out, that's a property, and then I'm going to rewrite 1 over cosine squared as secant squared of t dt. This is what I'm telling you about the fact that why you need to know your derivatives. If you know that secant squared is something, okay, then it'll make sense to you to rewrite 1 over cosine squared. If you don't realize that's anything, you're not going to see what to do. So if you have not focused on your derivative formulas like you should, make yourself practice every day for 10 minutes. It's not a big deal, but practice, practice, practice. Now the problem is super easy. So remember, constants in front. Well, what do I take the derivative of that gives me e to the t? Well, remember, that's the easy one, e to the t. Now, the plus c can just go at the end of this entire expression. I don't need a plus c at the beginning and a plus c at the end because plus a constant's plus a constant. Okay, so at the end of this problem, at the end of doing the antiderivative, there's a plus c. Okay, so then I do plus. Now I want to integrate this. Well, again, if I know my derivative formulas, this is easy. I know that the derivative of tangent is secant squared. So therefore, I know if I integrate secant squared, I should get tangent. Be sure you're using the same variables. So they were t's, and then my entire answer needs plus c. Now, do not forget your plus c's. Do not say to yourself, oh, I'm not going to practice that. I'll just remember. Because on a test, you're going to get a point off every time you miss plus c. And you might have a test over integration that has 8 or 9 problems on it like that. So you might miss 8 or 9 points just because you didn't write plus c. Formula quizzes, they will be wrong if you don't write plus c. So make sure you pay attention to that. Okay, so the important part of how I do integration is I have to write it so it's something I know how to do. I do not have a formula for some function squared. I have one for x squared, but not a function squared. So what we're going to do on this one is we're going to rewrite it. I'm going to just move over here so I can do it bigger. So I'm going to rewrite it. So what I'm going to do is I'm going to multiply out that polynomial. And remember, before we learned the chain rule, we did that for derivatives. So it's 9x squared minus 6x plus 1. If even for a moment you forgot about that middle term, make sure you practice that and really think about that carefully. Now I want to just do each antiderivative as I go across on a plus c at the end. So first let's look at 9x squared. So our rule is add 1 to the power and then divide by the power. Well, I have a 9 in front and then I'm going to divide by 3, so that makes a 3. Now, if you will look at these and you will work them back, okay, like do your derivative formulas, it'll help you see these faster. So if I was doing the derivative, I would multiply the 3 times the 3 in front. There's my 9. I would write this down and I would lower the power by 1. And there you go. So it will help you to sort of match things up if you'll just practice that a little bit. Okay, so minus. Now I have 6x. So again, x gets raised to the second, and then I would divide by 2 but I have a 6 in front. 6 over 2 is 3. Again, do the derivative, and you'll see how that matches. Plus the derivative of 1, which is x, of course, derivative of, or integral of 1, sorry, which is x, and then plus c. Okay, so you'll get faster and faster and faster at these. Okay, so like when we very first started derivatives, we kind of did the same thing here. We said, hey, I don't have a way to do this, so I need to rewrite this. Now, here is something really important that you really, really, really need to listen to. There is no quotient rule for integration. Very important. There is no quotient rule for integration. So I cannot integrate a quotient unless it fits a formula or I rewrite it until it fits a formula. Okay? So I cannot integrate that by some technique like with derivatives where we have a formula for quotients. There is no quotient rule. So really important. So what I'm going to do is rewrite this by taking this single, this monomial, and dividing everything on top by that monomial. And I'm going to write everything as powers, because just like derivatives, I got easy work if I have a power here, okay? So we have x squared over x to the 5th, that's x to the negative 3, plus 4 times, you have x over x to the 5th, so that'll be x to the negative 4, plus 5x to the negative 5, and then all of that dx. Again, don't be lazy. Make sure the dx is there. Now, the reason we could do that, again, is we divided everything on top by the x to the 5th. Now, let's follow our rules. So our rules for power say add 1 to the power, so that's negative 2, and then divide by the power. Plus, leave the 4 alone, have your x, add 1 to the power, divide by the power, plus 5x to the, add 1 to the power, that's negative 4 over negative 4, plus c. Now, you could stop there because you should be able to match this, but just to be sure that everybody does this correctly, I'm going to put all the negative signs on top just because in math we kind of prefer that. It doesn't matter. It's not a rule that you can't have them on the bottom, but usually we put them on the top. The 2 is in the bottom. X to the negative 2 means x squared in the bottom, so that means there's only a 1 left for the top. Now this is the one I want to be careful about because a lot of students want to move the 4 to the bottom. But the 4 is not being raised to a power, the 4 stays in the top. I'm going to move the negative to the top. I'm going to leave the 3 in the bottom. So the 4 and the 3 don't change. They're normal numbers like they've been your whole life. They don't change. Exponents work different. So x to the negative 3 is the same as x cubed in the bottom. Okay, and I'm going to do this again. So again, the 5 over 4 do not change. And then my x to the negative 4 becomes x to the 4th in the bottom, and then plus c. Okay, so I do need to be able to pay attention to that to know I can match that. So if you're not very good with positive and negative exponents, I would definitely practice that. Okay, so on this one, we're going to have to do more than one thing. So the first thing we'll need to do is multiply out that top because I don't have a rule for something squared and especially over something else. So the bottom I'm going to write as a power, but I'm still not, I don't have a quotient rule, so I'll have to rewrite after this step. So the top I'm going to multiply out, okay, and then still my dx, but I still can't do it the way it's written because I don't have a quotient rule. So now I'm going to redo it, and I'm going to have x squared over x to the negative, or x to the 1/2. So that's x to the 3/2, because that would be 4/2 minus 1/2, minus 6x to the 1/2, because it's x to the 1st in the top, x to the 1/2 in the bottom, plus 9x to the negative 1/2. So everybody got divided by x to the 1/2. and now everything's a power. So now I'm just going to go through it. Now, here's what I would do every time you have a fractional exponent. So leave a space in front for a second. I'm going to write x, and I'm supposed to add 1 to the power. So I need to think 1 is 2 over 2 for this fraction. So 3 over 2 plus 2 over 2, 5 over 2. Now, I'm supposed to divide by 5/2, but since I'm going to do this a lot, I'm going to remember that dividing by 5/2 is the same as times 2/5. So when you have those fractional exponents, you need to practice consciously going immediately to times the reciprocal. Okay, really important. Okay, minus, I'm going to leave the 6 alone for a second. I have x, I'm going to do the power. So again, I have to add 1. So instead of 1/2, I'm going to add 1, and I'm going to get 3/2. Now I need to multiply by 2/3. So I'm going to write it as 2/3 times 6. Okay, and after a while, you'll get pretty good at simplifying those without having to write it. Plus, again, I'm going to kind of leave the 9, or leave some space. We'll write the 9 here. And then x. Now I have to add 1. So I add 2 over 2. That gives me 1 over 2. I need to divide by 1/2, which means times 2, plus c. Now, this should be far enough for me to match something, right? Because I've got the answer. But I'm going to go ahead and simplify it for those that, especially that struggle a bit with fractions. So you need to remember what to do. When you do 2/3 times 6, you should never write 12/3. You should remember that there's a 3 in the bottom and a 6 in the top, and in your head, you should divide that. We're going to work with fractions a lot, and we need to be quick at it. So you should think that in your head and not necessarily write it, and know that that's minus 4x to the 3/2 plus 18x to the 1/2 plus c. And remember, do not change the square roots or anything like that, because fractional powers are kind of better. Okay, so I am going to skip looking at these questions where you're matching these things up. So we're going to skip that. And then we're going to talk about basically what it means to solve a differential equation. I'm just going to do a little example, one example, and then we'll finish the rest of this in class. So a simple differential equation is like dy dx equals 3x squared. A differential equation simply means there's a derivative in the formula, and I'm trying to get rid of the derivative and go back up to the regular function, okay? So for now, we're only going to learn how to do them in a really simple way, but we're never going to do any other method than what is called separation by variables. So I'm going to go ahead and do it that way and talk about it that way so that it's easier for you to figure out. So instead of writing f prime of x, we're going to write dy dx equals 2x minus 1. Okay, so this is again what we call a differential equation. The one and only way we're going to learn in this calculus class to solve those is by what we call separation of variables. So what we're going to do is we're going to leave the dy on the left, and on the right we're going to move the dx. So we're basically going to multiply by dx. Then I want to solve this, so what I'm going to do is I'm going to do the same thing to both sides, which is very normal, and I'm going to integrate because I need to get rid of the derivative. So to get rid of it, I need to go up and I need to integrate it. So the integral of dy is y, technically plus c, but again, we don't need plus c twice, so we're just going to put the plus c on the right. So I get y equals, the integral of 2x is x squared minus the integral of 1, which is x, and then plus c. So this would be what we call the general solution, okay? So if you're asked for a general solution, this is it, and I would be done. However, I can get the exact solution that works because I have an initial condition. I'm told that f of 2 equals 5. So I can actually find c by plugging in 5 for y and 2 for x. So I will use 5 equals 2 squared minus 2 plus c. So 5 equals 2 plus c, so c is 3. So what that means is the specific solution is y equals x squared minus x plus 3, because I just found the value of c and it is 3. Now, technically, I should write, because the original problem called it f prime, really I should probably write it like this, okay, that f of x equals, okay, so just going back to the beginning, it called it f prime, so we probably want to stick with that when we give our final answer, okay, and just use the variables that they used. So we will go over the rest of those in class, so that's it for this video.